So let me start with the outline of this this talk or this presentation. I will first show just some motivating examples of what can be done in the software, what results you will receive. Then I will go just through 2 slides of theory of the finite element method. And then I will show some examples of finite element meshes and show how a good mesh should look like, and etc. And then I will show you what types of finite elements are implemented in GEO5 FEM and which are used for which structural elements. And then the core of this webinar is, of course, the hands-on modeling. We will model a simple top-down tunnel and look at the results. Finally, I will come back to this presentation and show you some pros and cons of the finite element method in geotechnical problems in general. And also I will show you the types of analysis, of different types of analysis that can be done in the software. And finally, we will run this discussion section. So, for example, a very simple problem that you can solve is the displacement field, or we are always calculating the displacement field in the finite element method. So this is just some surcharge on the top of the terrain. This is the stress field, the vertical component of stress, and some deformed mesh and deformed terrain of the in the model. Another quite typical problem is a retaining wall. Here you can see the field of plastic strains. So there are some plasticity developing at the bottom of the wall near the tip of the anchor, and also there was some let's say slip surface developing over here before the anchor was applied. Then this is a stability problem, so some embankment with surcharge on the top, and here you can observe the failure mechanism and the plastic slip surface developing over here. You can also analyze tunnels over here. Again, you will get a displacement field, internal forces in the lining, and some plastic regions around the tunnel tube. Or you can solve water flow problems. This is a different type of analysis. So this is a transient water flow analysis. So basically, you are analyzing how the groundwater table and the saturation of the earth dam will develop when you change the original position of the water in the reservoir to this new level. So the earth dam gets saturated. Okay, so some basic concepts of the finite element method. The finite element method basically gives us an approximate solution to a boundary value problem for some differential equation. This is quite a general. So what the boundary value problem is? So it's it's kind of mathematical problem where we have some domain with almost arbitrary shape, and we have some boundary conditions. So here, for example, the displacement is prescribed. Here, the displacement is prescribed. There are some directions on the body's surface, on the body's boundary, and there are some prescribed body forces, for example, gravity in the body. And we are trying to find such a displacement field, so a displacement at each point, so that in example or in case of static problems, the equilibrium is satisfied at each point of the domain. So specifically in mechanical problems, we are trying to find such displacement field that the strain given by the geometric equation creates the stress by this constitutive equation that is in equilibrium with the external body forces. So this is the system of our differential equation, or this equation forms one differential equation that that has to be manipulated mathematically to receive a weak form, and which is then discretized on some finite element mesh. So we arrived to such system of linear equations. So you will not see these quantities in the software directly, but I think it's quite useful to keep in mind that the software in the end solves this system of equations. So we are looking for nodal displacements, R, and the software assembles some stiffness matrix and some vector of nodal displacements on the right-hand side. Okay, so let's go to the examples of finite element mesh. So this is, for example, some triangular finite element mesh. If you look at it, maybe some these elements in this area, which is not that interested, we are not interested in very much for some detailed results over here. So the finite elements could be a little bit larger over here to save some computational time. On the other hand, if you look at some details of the geometry, there are some points somewhere that probably don't have to be there, or this point probably. And it is always to have this geometry clean before we are creating the finite element mesh, because with this point we received these narrow pointed triangles that can cause, in some cases, they can cause some numerical problems. So try to keep your model as simple as possible and not to model any unnecessarily details. Okay, so another geometry. This looks like some problematic places over here. 2 points very near. Again, here a tangent lines. There will be some pointed triangles over here, which can cause problems. So the mesh could be nicer at some of these places. The last example, again, these are 2 tunnel tubes. Again, probably here there will be some problems, maybe a little bit, but the mesh around the tunnel tube looks quite okay. This one. Okay, so this was just some word about the finite element meshes. So it is also, I think, quite useful to keep in mind that not just these triangular or quadrilateral elements compose the finite element mesh. Of course, we have these. This is, for example, a linear triangular element. Each node has 2 degrees of freedom, horizontal and vertical displacement. Or we have these multi-node elements with nodes, with more nodes, which provide more detail and more accuracy. But we also have implemented in the software some 1D elements for beams. So these elements are used for structural elements that has some bending stiffness, like beams or walls or rows of piles or some continuous slabs. And these elements have 3 degrees of freedom, so axial and perpendicular displacement and also rotation. So these are beam elements. Then you have rod elements that are used to model structural elements like anchors, nails, reinforcements, or probes. So elements that are loaded in tension or compression. And finally, we have contact elements. Contact elements like this one consist of 4 independent nodes, but these 2 nodes are basically at the same position, but they have different degrees of freedom. So you can use these contacts to model a relative displacement between, let's say, your concrete wall and the surrounding soil. So there can be some slip between these two domains, and this is what contact elements allow. Okay, and finally, this is how these elements can be composed together. So basically, for example, this could be a wall, a retaining wall composed of beam elements. This is the blue one. This is connected where the yellow one, contact elements to the remaining soil. And we also have some rod, which is probably some anchor or nail. And this one is implemented here as so-called free element. So it's not connected to the original nodes. It's connected somewhere in the middle of the beam element and in the middle of the triangular element. The advantage of free elements is that you can put them into your model after you have created the finite element mesh. So you don't have to know the position of the anchor in advance. So here we look at the tunnel that we will model today. So basically it's a top-down tunnel. Two tubes, it's constructed this way. We first make a shallow excavation, then we construct these three diaphragm walls and put the concrete slab on top. Then we cover everything with soil again and reconstruct everything on top. And then we excavate left and right tube and create this floor and load the model. So this is basically what we will do. We will have three layers of soil, and basically that's it. And here we have the parameters of the soils. So first, second, and third soil layer, all of them will be modeled with more Coulomb material with some unit weight, Young's modulus, Poisson ratio, saturated unit weight, unloading and reloading modulus, angle of internal friction, and cohesion. So these are the results, and the concrete structures will be modeled with this material. So let me start the software. And first of all, I will save my my files. So, okay, desktop probably. Tunnel. And we can start. Looking what controls we have in the software. So first of all, we create a topology or a geometry of the model here in this topo view. On the right, we have so-called frames or views. So in the project, we can define just some metadata if we wish about our project. Then we go to settings. In settings, we don't have to change anything in this simple example, but it's always good to see that we are solving a plane strain problem, not an axisymmetric one, and we are running this stress analysis, which results in displacement field and stress field, strain field, internal forces, etc. We can leave everything else as it is by default. Then we go to interfaces. Interfaces is the frame where you define the size of your model and the soil layers. So first, click to set up ranges, and horizontally, the range of our model could be from minus 30 to 30 meters, and the depth of the model below the deepest interface could be 10 meters, something like this. We will see what the number means in a while. And then we will create these interfaces and the first interface will be at the 0 level, so from here to here. Then we will add a second interface. I think the thickness of the first layer was 6 meters, so it will be at minus 6 meters. And the last interface is at 13 meters. Here, 13 meters, I think, over here. When you click the last interface, the bottom of the model is automatically created those 10 meters below the deepest interface. So we created interfaces, and then we can go to soils. Again, here in topology, you basically define the geometry, the soils, and then you create the finite element mesh. And then we continue with construction stages, because in finite element method, we don't model a single state of the structure, we model the construction process. Okay, so soils, we add the first soil, which I think is so A. The model is more Coulomb. This was, I think, 19. This was 20. The stiffness according to depth was kept constant, 0.35. I think the saturated unit weight was 20. We will not model water or the groundwater table here, so it's probably not necessary to enter it, but yeah. Then this was 20, I suppose. 20. Angle of internal friction was 29, and cohesion was 8, I hope. And we can choose some color over here. I will go to presentation and 20, 29, 8, 20, yes. Okay. So we click add, and we have this over here. Then I will create the second one, which I think is almost the same. This is 40, I suppose, 40. So 120, 31, I think was the angle of internal friction, and cohesion was 4. You can click and we create this with a different color. Click OK, and we have created the second soil, and finally we created the last soil, which has, I think, 80 megapascals, the Young's modulus. Then everything is the same. This is 30, 33, and 0 cohesion and 0 dilatancy angle, and a different color. Okay, so we have created these 3 soils. I hope I have entered what I wanted. Then you could go to rigid bodies. Rigid bodies is basically a different kind of material, which is basically rigid, and it differs from the soils that some of those quantities are not plotted in these regions. Then we go to assign, and here in the assign frame, we just assign these soils to those domains. So if you just hover over the soil, you can observe its name. So this is A. A is selected, assigned to this place. This is selected over here, and this is selected over here. And if we have some contacts in our model, we don't. We could define their parameters over here. Lining, we will not define a lining anywhere here, but we will enter the geometry by these 3 points and 3 lines. 3 points and 3 lines are more flexible than interfaces. Interfaces are mostly intended just to model the soil layers, while the 3 points and 3 lines are here for modeling of the structural elements mostly. So I click Add Graphically, and I will first add these points. So one, I think, should be over here, one here, then another over here and here, I think, so that it corresponds to our geometry. You can also import a template from some DXF file, and then you just click at those points, so you don't have to measure, see those coordinates. And another point, I think, is over here. And the last points over here, and here. So we prepared the 3 points, and we will then connect them here in the 3 lines frame. So click Add Graphically, click over here, and again, just connect these 2 lines or 2 points to create the geometry. And finally over here. So I think this should be our geometry. Very simple. And we can go to finite element mesh generator over here, click Generate. So this will generate a finite element mesh with the element size of 1 meter, or a typical edge of the element should be 1 meter. So it would look like this. Again, probably we don't have to have some great details near the edges of the models. We are more interested on what's happening around the tunnels, so we can make the mesh, let's say, a little bit more coarse, or the element bigger at the boundaries. So we can come back to the line refinements, and we will use them to change the element size here on the left boundary. So the radius where we change the element size will be something like 12 meters, and we prescribe the edge length to 4 meters, something like this. And we prescribe the same over here. And also here at the bottom. Could be something like this. So these areas should have larger elements. We come back to a mesh generator and regenerate the mesh. It looks like this. Okay. So I think this completes what we have to do in the topology. And we can go to the first stage. In the first stage, you should do nothing else than to compute the geostatic stress, which basically means just to run the analysis with the original soil layers. But we can go through all these frames. So activity means which part of the model is active. Assign, we can reassign the soil here if we want, but this is correct now. It's inherited from the topology, so we won't change anything here. No water, no structural elements should be present in the first stage, so we can go directly to the analysis frame and around the analysis. Okay, here we see vertical stress. We could go through these results. We will go through these results later. So what is, I think, quite important to note that in the first stage, the displacement, vertical and the horizontal displacement field is zeroed. So this is, let's say, the undeformed state from which the analysis starts. So basically, you should not model anything important in the first stage. You just create the initial geostatic stress. Okay, so this is finished. We can go to a second stage. In the second stage, we will probably excavate this top part. So we will not use excavation feature. Excavation feature is only related to tunnels, to the so-called beta method when you model driven tunnel in 2D software like this one. So this is related to tunnels only. So we just deactivate this upper domain or this upper section. So we click here inactive and click this one. It's red, so it's deactivated. We go to assign. This is our model now. The cells are assigned correctly, and we just run analysis. Okay, so this is again a vertical stress. Vertical stress is of course 0 on the new terrain. Okay. We can also have a look at how it deforms. There is a slight upwards motion or heave of the this bottom line. So we can go to next stage. So we add a new stage, and in this stage we will create the diaphragm walls. So these underground walls will be modeled as beams. So we click beams in the third stage. We click add graphically, click on the line, and enter its cross section. The cross section of the beam can be a rectangular wall, which basically means we are computing a 1 meter slice of the model always, or a pile curtain. Then you have to specify spacing of these piles, etc. So rectangular wall is what we need here, and I think the it's 0.8 meters thick. 0.8 meters thick. It's made of concrete, and you can choose your concrete over here. So there is some cross section, some material. We are not going to introduce a contact on the left or on the right hand side. This is necessary to. It is necessary to introduce contact. Let's say if you have some retaining wall that can separate at some places from your soil. So if you want to prevent a tension on the contact, you should define a contact over there. There are a compression over all around the tunnel in this case, so it is not necessary. So we created this beam. Click OK, and then if we want to specify these beams on the other lines, it's quite useful to highlight your existing beam, and then if you click to new line, all these properties are inherited. One thing that I forgot to comment on is are these supports. So the beam can end with either a fixed end or a hinge, or some sort of a tip. Okay. So we will add these beams over here and here. And here and here. Okay, and we are under analysis again. Go to analysis, analyze. So again, we introduce some stiffness into the model now, and some loading. The loading is the self-weight of these beams. So if we look at vertical displacement, for example, so there are some there is some vertical displacement. If you want to see what changed from the previous stage, you can go to this option and choose compare to previous stage. So this is only a relative displacement caused by the introduction of these diaphragm walls. Okay. So we click at another stage, and another construction stage is constructing of the slab, creating the roof of the tunnel. So we go again to beams, and graphically. Sorry, I will highlight this one and click this one. So I have the same stuff over here, and I just change the thickness of the slab, or the yeah. And this is the same. So in the fourth stage, we have created this slab on top of the terrain. We still have, if you look at activity, we still have the soil active below, and we can go to analysis and analyze. Again, there is some displacement due to the loading of or due to the self-weight of this slab. Then we, I think, create a next stage in which we activate, this inactive domain again. So we could go to assign. We could put another soil in there as some different backfill, but for simplicity, I just switch this soil again on. So this means that yeah, we put the soil back. I think it's quite clear. Again, we go to analysis and analyze. So by these small steps, you follow the process of the construction. This is typically not necessary to do with elastic models, but here with elastoplastic models, the sequence of the construction steps can be quite important in some cases. So you should follow the construction process in your model as well. So we add another stage in which I will put some surcharge on top. So I will put some loading, some distributed loading here on terrain. I will add it textually. It will be a strip surcharge positioned on terrain. It will start on, I think, minus 14, and the length will be, I don't know, 20, 25 probably. And the magnitude would be 30 kilonewtons per square meter. click OK. Cancel. So this represents, let's say, the loading of the terrain by traffic or whatever. Again, run analysis. And we can continue with excavations. Again, in this seventh stage, we would like to excavate the left-hand side tube. But again, we don't have to use this excavation feature. If you look at the excavation feature, if you add an excavation, there is the activation in this seventh stage in persons, which is what is called a lambda or beta method or convergent confinement method. And this is done or this is used only for driven tunnels, which are obviously not 2D problems, but this is some numerical tool to analyze those driven tunnels in 2D software as well. So we are not going to use excavations. We will go to activity and just deactivate, click inactive, and we state that these two domains are inactive. And again, go to analysis and analyze. Okay, again, we have some displacement field, some plastic regions where they develop. You can see, you can also look at, for example, the internal forces in the beams at this stage. So if you click this gear button and select beam variables and choose a moment, you will see a bending moment. You will see a bending moment on the structure at this stage. And to be it better visible, you can switch off these isosurfaces, these colorful images of the quantities. Okay, so this is the bending moment at this seventh stage after we have excavated on the left tube. So we can go to another stage and obviously to deactivate the rest. Go to analysis. Okay, then we can go to we will add another stage and we will create the floor in the tunnel by adding a new beam. So again, and graphically on this line, but I think it's just 0.6 the thickness. And this one the same. And go to analysis, analyze. And finally, so these are the bending moments. Finally, we can apply a surcharge or distributed loading on the floor as well. So probably at another stage. And because here we are loading not the soil, but the beams directly, we will use beam loads over here and graphically to this beam. you can apply a load that is uniform on the whole beam, is perpendicular, and its magnitude would be 30. And 30. Again, NV around the last 10th construction stage. Nice. Okay, so these are the internal forces or bending moments. We have all these horizontal displacement, vertical horizontal displacement, and we have to show them horizontal displacement, vertical displacement. Shear stresses, if you wish, plastic strains, etc. We can also use so-called monitors, if you wish. So you can add a monitor, which is a point somewhere in your model. So let's say you are interested in, let's say, this this point, how it behaves. So put a monitor over there. And then if we have this point edit, now we can see that the displacement is this and this. And we can also add a graph, which basically means show me how some quantity developed in this point during the analysis. So on x-axis, I can have a course of loading, which means basically what how this quantity developed in first stage from 0 to 100% of applied loading, then in second stage, third stage, etc. And here we can have, let's say, a settlement vertical displacement. And then when you select the point, you can see that nothing has changed in the first stage, because this is the stage where the geostatic stress is generated and the displacements are zeroed. So then the material wasn't there, so the line is not here over here. Then we put the backfill over there, and we start on this displacement, and this is how it develops when we apply the loading and make these excavations. So this is basically, yeah, how the displacement was developing at this place. Okay, I think this could conclude what we have done here. Maybe we could just look at what would happen if those joints over here would not be a fixed joints, but let's say hinges. So I will save this. Maybe I will save a new file. And I will come back, I think, over here, and then we can edit these beams. I think of this one, and we will put a hinge over here. I don't know if it works like a hinge or not, but just to show you what you can define in the model. Again, this would be a hinge. Okay, and again, there would be a hinge on top. Okay, and then I think everything else is the same. So let's start. Maybe we'll compute it up to this 7th stage only to save some time. Go to analysis, And if you run analysis in this stage, it will recompute all those stages that are not computed before. So we are now calculating the third stage, fourth, fifth, sixth, and seventh. And we will look at the internal forces, or especially the bending moments over here. So just some experiment. Again, I can switch over the isosurfaces. So there is one, I think 1550 over here and 0 at the hinge, which is, I think, natural. And so I will save this, and we can compare that to that moment of the previous model with fixed, it was 7th stage, I think. And again, we can go to analysis and switch off the isosurfaces. So there is something like 726 and 128 at the corner. So different values, different structure, different results, different distribution of internal forces, obviously. So I think this concludes this example, this hands-on example. As I said, we will send you these 2 files so you can experiment with them as you wish. I think you can even experiment with them in the demo version of the software. You can load the program. I think the demo version is limited so that you cannot save your files, but you can run the analysis the same as I'm doing here. Okay, so I will go back to the presentation, and yes, so here I would like to mention that just some differences between the calculations according to design codes and the finite element method. So the finite element method, its advantage is that you can have problems with almost arbitrary, in our case, in plane strain or axisymmetric problems. So that's a great advantage, and that's why the finite element method was developed mostly. The second advantage is that you can analyze multiple phenomena in one system, in one software. So you are getting a displacement field, internal forces, plastic regions. You can observe the possible failure mechanism, etc. And one characteristics of, I would say, all the softwares based on finite element method is that they are based on physics and not on the design codes, which I don't know if this is advantage or not. It's a fact. So and you have to deal with this somehow. So for example, you don't have any design coefficients, for example, those known from Eurocode. So you have to multiply your loading by a proper coefficient by hand and enter it to your software, or you have to divide the strength of the soil by, again, a proper coefficient. And also because there is a lot of things going on under the hood of the software, it's generally prone to this garbage in, garbage out issues, which basically means that you always should know what you are doing. Some example of this could be this example. For example, if you have just a shallow excavation without any retaining wall, just excavation of this part of soil on the left. And if you model your problem with elastic material and constant stiffness, you will arrive at this displacement field. Here we draw horizontal displacement. So you can be surprised why, if I excavate on top, why I have this large displacement in the middle of my model. And this is obviously not a correct solution. This is obviously not how the soil behaves. It's unrealistic, but it is a correct solution of the problem, because if this material is elastic and it has constant stiffness, you can think of this model not as being a soil, but as being some kind of, let's say, a jelly in some box. And if you cut out the jelly from this box, it will flow directly this way. So the material will, say, flow or deform this way. So the largest displacement will be in the middle of your box. So on the right-hand side, there is something that is more realistic. Basically, this is the same model. There are just two things in which these two models differ. The second one is modeled with a Drucker-Tager material model, which is some simple elastoplastic model. And we also have a stiffness increasing with depth, which is obviously what or how a normal soil behave. The more you stress the soil, the stiffer it is. So, and this can be translated into the Young's modulus, or the stiffness of the soil increasing with depth as well. So here again we have this phenomena here as well, because the soil is still elastic. So what has happened here happens here as well. But because of the plastic strains, we have this kind of deformation, which is definitely more realistic. Probably here are some plastic strains, so some slip surface develops over here. And finally, I would like to go through the GEO5 FEM types of analysis, which basically corresponds to modules that you can have to supplement your software. So what we have done today is a stress analysis. We see the stresses, strains, internal forces, etc. Then we have a stability analysis that can give you a factor of safety and some possible failure mechanism. Another option is, as I mentioned already, is the so-called convergence confinement method, which is used for driven tunnels. Another type of analysis is consolidation, which is basically time-dependent displacement due to a dissipation of excess pore pressure. And then we have earthquake analysis, in which you have a dynamic and model analysis of the soil loaded by some earthquake. And finally, a waterflow analysis, which is transient or steady state, basically a transport process of the water through the pores. So the results is, for example, a groundwater table or pore pressure field, etc.